In section 7.2, we're going to start talking about the central limit theorem for sums. So, just like with the central limit theorem for means, the central limit theorem for sums says that if we take larger and larger samples and find their sum, so we're just adding all the values from the sample together, then that sum will form its own normal distribution, or the sums form their own normal distribution. So the normal distribution will have a mean equal to the original mean multiplied by the sample size, and a standard deviation equal to the original standard deviation times the square root of the sample size. So in symbols down here we see that the mean of sigma x, remember sigma just refers to a sum. Anytime you see a capital sigma, that's a sum. So the mean of the sums of x is just the sample size times mu. The standard deviation is the square root of the sample size times sigma. So this changes our z-score formula a little bit. Similar to the way it changed with means, it changes again here for sums. We see that now we have sigma x minus n times mu divided by sigma times the square root of n. So just keep in mind that with means, it's sigma divided by the square root of n for the standard error. But this time, the standard error for sums is sigma times the square root of n. So first example, we have an unknown distribution. So we don't know if it's uniform, normal, skewed one way or the other, exponential, we don't know. So we have an unknown distribution with a mean of 90 and a standard deviation of 15. A sample of size 80 is drawn randomly from the population. Part A asks, find the probability that the sum of 80 values is more than 7,500. So in symbols, here's what we're trying to find in part A. The probability that sigma x is greater than 7,500. So we apply our new z-score formula. So 7,500 minus, this is 80 times 90. 80 is the sample size, 90 is the mean, divided by 15, standard deviation, times the square root of 80, sample size. So this gives us a z-score of 2.24. Going to the table, we see that we have an area to the left of 0.98745. But again, this is a greater than question, so we don't want to use that number. That number is a less than answer. So to find the correct greater than answer, we do 1 minus that, and it gives us 0.01255. Part B of this question asks, find the sum that is 1.5 standard deviations above the mean of the sums. So essentially, remember what the z means, right? The z tells us how many standard deviations something is above or below the mean. So we work it out like this. Okay, we set z equal to 1.5, and then we plug that into our formula, and we're looking now for sigma x. Okay, we're trying to figure out what is the sum that's 1.5 standard deviations above the mean. So working this out, the first thing we do is multiply by that 15 times the square root of 80 on both sides. It gives us 201.246 equals sigma x minus 7,200. We're going to add 7,200 to both sides, and it tells us that sigma x is 7401.246118. We'd probably round that to, we might just round it to 7401, maybe 7401.2, kind of depends. If we know how many decimal places the original data carried, then we'd probably go one more than that. But we don't really know for sure, so never hurts to have too many decimals. For example number 2, we have apparently a recent study, which is 2012, so it's not that recent. Says that the mean age of tablet users is 34 years and the standard deviation is 15 years. The sample size in question here is 50. So we want to find the probability that the sum of the ages is between 1,500 and 1,800 years. This is maybe not the world's greatest example, because I don't know why you would want to find the sum of ages. Mean seems like it would be a better choice here, but I guess sometimes you just got to go with the examples that you have. So for whatever reason, we're going to add all these ages up. We want to know what's the probability that the sum is between 1500 and 1800. So in symbols, this is what we're dealing with. And we're going to find two different z-scores this time. First, for the 1500, okay, using our new formula for central limit theorem for sums. Then we're going to find a second z-score for the 1800 value. And we need to know from our table, what did we get for, what's the area to the left of negative 1.89, what's the area to the left of 0.94. Instead of showing you pictures of the table again, because these values are way out in the middle of the table and it would be hard for me to show you the left side column that tells you the base number and then the top row that tells you the hundredth decimal. So anyway, just trust me that these values come from the table, and what we need to do to find the probability between them is we just need to subtract them. So subtracting 0.826 from 0.029, we get 0.797. So that's our probability for question A. Question B asks us to find the 80th percentile for the sum of the 50 ages. So we're trying to find P80. And what I'm going to do is I'm going to look in the area of the table where I can get as close to 0.8 as possible. And looking at this portion of the table, I know you can't see the left side column or the header there at the top, but this value 0.79955 is the closest value that we have, and it's pretty close, within 5/10 thousandths of the true value. So that's the one we're going to go with, and that gives us a z-score of 0.84. So now I need to turn that 0.84 into a sum. So I set 0.84 equal to my formula here for the central limit theorem for sums, and I'm trying to find sigma x. So again, multiplying by 15 times the square root of 50, and then adding that 34 times 50, I get that's the sigma x is 1789.1, and I did round this one a little bit. Anyway, this would be our 80th percentile value for the sum. Your suggested homework for section 2 is some practice problems, 7 through 10, 16 through 21, and 31 through 33. This is just a few questions from a couple different headings, a couple different scenarios. So let me know if you have any questions on this one.